that we have two classes of amino acids. We have essential amino acids and we have non-essential amino acids. And the difference between those is that essential amino acids we have to get from dietary sources. And that simply means that we cannot synthesize those amino acids. The non-essential simply mean that we can make those amino acids. Now, here's the synthesis of our 11 non-essential amino acids. They come from different products. Most of them are coming from the energy generating pathways. And what we're talking about here are the carbon backbones. So the carbon backbones are synthesized, and then we have to add the nitrogen on the alpha carbon to make the full complement of the amino acid. But the pathways are rather complex. Now, there's a few simple pathways that you already know already. So if you want to make the amino acid alanine, you're going to extract carbons from the energy pathway in the form of pyruvate. And then you're going to use ALT, alanine transaminase, to add an amino group onto the pyruvate. You get alanine. Boom! Very easy. That's synthesis of alanine. Aspartate is the same way. So aspartic acid, we're going to use oxaloacetate, transamination, put the amine on there, you have aspartate. You can make asparagine from that by adding an amino group to the end of that R chain, the side chain of the amino acid. Okay? So logically, there's a few patterns that you can recognize. Glutamate, glutamine are the same ones. Now, when we get into some of these other reactions here, like serine and cysteine and glycine, we'll see these a little bit later next week when we talk about vitamins, because those are coming off of the vitamin pathways, especially for vitamin B9, which is folate. So what do you need to know about this? What I've determined is you pretty much need to know that your transaminase enzymes are reversible. So when you're breaking amino acids down, you can use the transaminases to get rid of the amine so that you get the carbon backbone. You take the carbon backbone, you put them into energy producing pathways. In order to synthesize amino acids, you need to get the carbon backbone of the amino acid, so you're going to extract those from energy producing pathways and put the amine group on them. So that's generally the flow without having to go through all of these biosynthetic pathways. Okay? So, that being said, let's move on to more interesting things. And I'll give you more patterns as we go. So the big thing about amino acids, and I'm sure most of you have looked at this in first aid, is that they focus, there's lots of information on amino acids. In the past in this block, I have not focused much on amino acids, just pretty much giving you some nitrogen balance and carbon, what's going on there. But then I started looking at the first aid, and I started remembering what was in the NBME database, and they spent a lot of time on amino acids, and it's primarily the disorders that occur. So let's start out with the easiest one that most of you pretty much already know, and that's PKU. So I started out with the easy one because this is a very, very simple disorder. So PKU is phenylketonuria, and the problem here is a faulty phenylalanine metabolism. Now what happens here? Phenylalanine, the amino acid phenylalanine, which is an essential amino acid. We get this from our diet. We can't synthesize it. But we can synthesize tyrosine from that. So how we're going to synthesize tyrosine is we're going to take our phenylalanine structure. Here's the name of phenylalanine. Here's your phenyl ring structure. Alanine means that we're just using this phenyl structure, this ring structure, and putting it on a CH2. We took this off. That would be the amino acid alanine. So we're just going to put the ring structure on there. That's phenylalanine. What we normally want to do is convert this phenylalanine to tyrosine. It's a single-step reaction. using phenylalanine hydroxylase. Okay, enzyme hydroxylase, you can pretty much figure we're must going to be doing some ACE to a product, a substrate, and putting a hydroxyl group on it. And that's what we're doing. We're going to put a hydroxyl group on the para position of the ring using this enzyme, and then we magically have tyrosine. Now, if we have a deficiency in this enzyme, phenylalanine hydroxylase, that is phenylketonuria, PKU. Now, the problem with this is that we cannot obtain our tyrosine from biosynthetic measures, so we have to get it from our diet. But worse than that is that we have a buildup. So this is exactly the kind of patterns that we've seen in all of our other reactions, both normal and pathologic. So in normal reactions, if we have biochemical reactions doing this, and this is something that I brought up to some other students that have come to my office for questions about a general theme to keep in mind about biochemical pathways. Whenever you come to a place where there's a branch, we have a decision point. So this point here is typically the regulated area. So that means that the decision point is going here. You can send this into one of two pathways. Now, when this happens, there's going to have to be regulation downstream in order to control which pathway is being used at any one time. So let's say that we are in the classic one that we've looked at is the cholesterol pathway, cholesterol synthesis, and fatty acid synthesis. We have our acetyl-CoA, which is starting at the top of our pyramid here. That's coming on down here. We get to this point here, and now we want to branch off and either form fatty acids or cholesterol. So if we need both of these, we're going to send substrate down both pathways. But if one pathway gets inhibited because of a feedback inhibition, so let's say that we inhibit right here because we don't need any more cholesterol. This, of course, is going to be the SREBP pathway that is going to be regulating this by downregulating HMG-CoA reductase. Now, whenever you inhibit a pathway, that means that the substrates prior to that inhibition point are going to start building up. And this is the problem, this is the interface of biochemistry and medicine. If a substrate starts to build up, and it has what I keep calling no escape route, that is when the product could become a toxic intermediate. Because everything that we have in our body, every chemical we have, could potentially be toxic to us. The levels are what determining toxicity. So as long as you have your substrate to product formation and you've got your biochemical pathways going, everything's fine because all of your substrate and product are being controlled, the levels. Once you have an inhibition, now things start backing up. In our case here, we have an escape route. And that escape route is here, going to fatty acid synthesis. Okay? What this means is that the HMG-CoA that could potentially be building up, creating a toxic situation because we're inhibiting the enzyme, that's going to reverse, and then we're going to put our substrates into fatty acid synthesis, and so we've got an escape route. So there's no buildup of any of these substrates in product. Now, that's normal. That's normal physiology, normal biochemistry. Now, most of these defects that we're talking about, these inborn errors, are a good example here in PKU. If you've got an inhibition of conversion of phenylalanine to tyrosine by inhibition of this phenylalanine hydroxylase, or deficiency of the enzyme, the phenylalanine builds up. Now, phenylalanine is an amino acid. The problem with this is that this, as the concentration increases, it will undergo a normal transamination reaction, and we will build up this phenylpyruvate. Now, the phenylpyruvate is nothing more than the alpha keto acid of phenylalanine. This is our problem. We have no place to go. We have no escape route with this substrate and product. And so this starts building up in the circulation. This is an acid, and we already know generally, our general rule, that if we build up acids in our circulation, we are going to decrease pH. That is toxic. And the other problem with this is that phenylpyruvate will compete for the uptake of phenylalanine. So even if you do have phenylalanine in the diet, this is going to outcompete as the concentration builds, and that is presumably what is thought to lead to the brain damage of PKU, is because the tissue is just not getting enough of that essential amino acid. Essential being from the diet, and we cannot synthesize the phenylalanine. Okay, so this is a recurring theme we're going to see, is if we've got pathways going, if we block them abnormally due to a mutation, it's the substrate that builds up that leads to the toxic intermediate. Okay, so that's PKU. Now, let's go back to our amino acid degradation. Because here's another general rule to think about where these amino acids are going. There's two types of degradation product for amino acids. They can be either what is called glucogenic or ketogenic. And this is probably the most important feature of amino acid degradation as far as amino acids and energy production. Because we're going to do our transamination, that's the first reaction, get rid of the nitrogen, and then we're left with the carbon backbone, and we're going to put that into energy producing pathways. Well, depending on the amino acid, and these are all listed in first aid, depending on the particular amino acid, you're going to break this down into a substrate for either glucose production in gluconeogenesis or feeding ketogenesis. So the difference in these products is that the ketogenic amino acids are going to break down into acetyl-CoA. The glucogenic amino acids are going to break into products that can enter the glycolytic pathway going backwards, which is gluconeogenesis, or they can enter the TCA cycle. And anything that enters the TCA cycle is gluconeogenic. Then there's a couple of amino acids that are both considered glucogenic and ketogenic, because when you break those down, the products of these can enter either one of those reactions. So that's probably the most important way to understand amino acid degradation in a physiological sense. And this is where I believe most of the questions will be in the MBME, right here. So here's another way to look at the degradation. If we have 3 carbon backbones on our amino acids, such as alanine, serine, and cysteine, they're going to each have their own individual degradation pathways. Alanine, of course, is the simple transamination reaction with ALT. And the resulting product of this is pyruvate. Breaking serine down, we're going to end up with pyruvate. Breaking cysteine down, we're going to end up with pyruvate. So 3 carbon backbone amino acids are broken down to a 3 carbon energy intermediate. So now are these amino acids glucogenic or ketogenic? Glucogenic, yeah. Because the pyruvate is going to feed into oxaloacetate production in the liver because we're in a fasting state. And our acetyl-CoA levels are already high to push it into pyruvate carboxylase. So those are primarily glucogenic. Now if we look at our 4-carbon amino acids, aspartate and asparagine. This, of course, is a simple transamination reaction with AST, and we are going to place this into oxaloacetate. So 4-carbon amino acids are being broken down into a 4-carbon energy intermediate. Glucogenic or ketogenic? Glucogenic, yeah. Because remember, oxaloacetate, as you're putting it into the TCA cycle, in the fasting state in the liver, this has only got one place to go, and that's to malate and then on to glucose. So let's beat this dead horse and take it even further. 5-carbon backbone amino acids. Glutamine, glutamate, proline, arginine, and histidine. All 5-carbon backbones. And of course, glutamate, you know, this is the single transamination reaction to give alpha-ketoglutarate, which is a 5-carbon backbone. So 5-carbon amino acid structures enter a 5-carbon energy-producing molecule. Glucogenic or ketogenic?
I think it's ketogenic.
This is ketogenic?
Oh, alpha ketogenic. Got stuck.
Yeah, glucogenic. Because again, this is going to go into the TCA cycle. The TCA cycle will process this all the way over to malate, and then malate out to glucose production. Okay? It's too early for this? I hear you. I've been yawning all morning long. This is painful. Okay, so now, let's get back to diseases. So those are kind of some rules, general rules that I think will get you through the amino acid metabolism exercises. So now, the next major amino acid problem that you need is a breakdown product. This is a degradation problem. And this is maple syrup urine disease. And that turns out to have a maple syrup flavor. Great for your pancakes, right? Will you ever forget this? No, never. Okay, so what is this? This is a degradation product of our branched chain amino acids. Branch chain. So what is a branch chain amino acid? Here they are: valine, isoleucine, and leucine. So here is the alpha carbon. I'll put a dot on the alpha carbon. And then to the left is the side chain of the amino acid. So valine has a carbon and then a branch of 2 CH3 methyl groups. How do you remember that? It makes a V. I just let you into my head how I remember it. It's kind of scary, right? So it's a branch chain. Let's look at leucine. Leucine is simply 2 carbons and then the branch like valine. That's leucine. Isoleucine is an isoform of that. So instead of having a branch chain, this has been removed and moved over to here, into this second carbon. And that's isoleucine. So these are the only amino acids with side chains with branches to them. All the other amino acids have linear structure to them. So the first step of these branched chain amino acids is this step right here. It's an oxidative decarboxylation reaction. The enzyme's not important. But just to know that this first step is inhibited. And by having this first step inhibited, these particular amino acids have no escape route. They have no place to go. And so their concentration starts to build up. And it builds up to toxic levels. Now, a couple more major breakdown products. So here's our phenylalanine. Here's our PKU. And of course, the inhibition of this is going to lead to the phenyl keto acid of phenylalanine, which is the toxic intermediate. The other two here, the first one is tyrosinemia. Now there's two forms of this, but I don't ever recall you having to differentiate the enzymes that cause this. This, I believe, is the big one right here, if I remember the numbers and statistics right. Tyrosinemia here is going to prevent the processing, the further processing of tyrosine in its degradation process. And this block is going to lead to elevated concentrations of tyrosine. That's tyrosinemia because the tyrosine concentrations start to increase in the circulation. Now there's two problems that lead from this, that result from this. One is that tyrosine is an amino acid. So again, there's no escape route for this, except that you might think, well, if this builds up, we have an escape route this way to the through the hydroxylase enzyme. Well, as some of it gets through because you're increasing the substrate concentration going the opposite direction, then phenylalanine starts to build up, and what does high concentrations of phenylalanine do? We shift into the keto acid, which is symptomatic of PKU. So again, same principle. We have a block here, and we have essentially no escape route. So the concentration of these builds up and leads to these toxic intermediates. The other one is down here, alkaptonuria. This is further along the processing of this aromatic amino acid degradation pathway. So we can get all the way down here to homogeneous state, and we have a block here. This is a toxic intermediate because 8, there's your acid. And so that's going to cause an aciduria problem. Now here's a good question about phenylalanine in tyrosine breakdown. If all these enzymes are normal, and you're able to break them down to their final product, is this ketogenic or glucogenic? Both. Yeah. Glucogenic, ketogenic. Okay, so the other disease is homocystinuria. And this problem here, homocystinuria, is a breakdown problem of methionine problem, mostly. And we will talk about this when we talk about B12 and B9 vitamins next week. Okay? I'll put that into a little bit more specific context. Now here's some more interesting biochemistry. I'm sure you learned a little bit about these in the renal block, right? Kidney stones? What type of kidney stones are there? Yeah. So there's a lot of different types, right? This one here are oxalate stones. And oxalate is simply this funky little molecule of a couple CO2s put together. And this comes from glycine degradation problems. So if you have excessive protein in the diet and you're pushing a lot of glycine through your metabolic pathways, you have an opportunity to increase the production of oxalate and cause kidney stones, one of the types of kidney stones.